Hey there, chemists. In this video, we're going to talk about how you form what are called complex ions and coordination compounds. Complex ions are just bigger ions that are made out of what's called a Lewis acid, that's usually a metal cation, and a Lewis base, which is also called a ligand. Anything that has a lone pair can act as a ligand or a Lewis base. There's many examples of them, and I just want to show you a few so you can see what they look like, what shapes they have, what geometries they exhibit, and then ultimately why they exhibit so many unique colors. We can even calculate what wavelengths are absorbed by these different kinds of complexes. So here's one made out of cobalt and just water molecules. This is what aqueous cobalt ion actually looks like. It has a coordination number of what's called 6, meaning there are 6 water molecules coordinated to the cobalt atom. So it's a 6-coordinate complex. Each water molecule is one ligand. We call that a monodentate ligand. And you might recognize the geometry. That's an octahedral geometry, just like we saw in the fall semester when you have a hexacoordinate system. Right below it is a platinum complex with 4 ammonias. That would be PT, 4 ammonias. Notice the overall charge is the sum of the charges of the reactants. 4 neutral amines, ammonias, and a platinum 2 gives you a platinum tetraamine 2+ complex. This is a 4-coordinate complex because there's 4 covalent bonds between the ligand and the Lewis acid. And unlike the tetrahedral geometry we saw in the fall semester, this one exhibits a square planar geometry. These are obtained empirically. There are certain rules for what geometry is exhibited by a complex ion based on the oxidation state of the metal and what the metal is. I'm just showing you some examples right now so you can see what they look like. Here's a silver complex. We've actually seen this in class. This is just with 2 ammonias, and you get the silver diamine complex that looks like that. That's actually the Tollens reagent. That's a 2-coordinate system, so it's a linear geometry because there's only 2 ligands on the central metal. Here's another 4-coordinate system with 4 ligands, so you get zinc with 4 ammonias, overall 2+ charge. Unlike the square planar one, you also can get a tetrahedral geometry out of this as well. So both tetrahedral and square planar are possible for 4-coordinate complexes. And you'll see that the ligand can vary as well. There's a lot of different ligands that are possible. There's a few of them in this chart over here. The thing that they all have in common is they all have a lone pair of electrons, at least one, that can form what's called a coordinate covalent bond to the metal. All of these ligands happen to be monodentate ligands. There's a couple examples of what are called bidentate ligands that are shown in these 2 examples. A bidentate ligand is one ligand, here's the oxalate dianion, and it forms 2 covalent bonds with the metal, in this case a copper ion. So because it's forming 2 bonds, but it's only one thing, we give it a special name. We call it a bidentate ligand. I'll write that down in a second. What does this complex look like? Well, that's 1 copper. This ligand is not neutral. It's got a 2 negative charge, and it picks up 2 of the oxalate. They actually abbreviate those with ox. And then notice the overall charge is the sum of the charges of the reactants. So 1 2+ and 2 2 negatives gives you an overall 2 negative. It's still a copper 2 cation, but the whole complex has a charge of 2 negative now. Sometimes they're positive, sometimes they're negative. You can also have a complex. This is a 4-coordinate, and that is a square planar complex. Here's another 4-coordinate copper complex with a different bidentate ligand. This is called the ethylene diamine ligand, abbreviated EN. And when you pick up 2 of them, you get a 4-coordinate square planar complex that looks like this. So there's a lot of different varieties of these. For the purposes of this class, I just want you to recognize that these are reversibly formed. So we'll talk about the equilibrium constant related to this. It's technically a formation constant, Kf, but it's just an equilibrium constant like any other equilibrium constant we've done in this unit. And it's written as bracket your products divided by bracket your reactants, and everything raised to its coefficient, just like every other equilibrium constant we have. And everything is aqueous, so everything gets included in the K expression. And back to this chart with some various ligands, we have a bunch of monodentate ligands. That means they can form 1 bond with the Lewis acid each. And then there's 2 that are bidentates, the oxalato ligand and the ethylene diamine ligand. There are many others, but those are just two that I want you to know for the purpose of this class because they're so common. So, ligands, which are these neutral or anionic Lewis bases, form what are called coordinate covalent bonds. And what that means is that all the electrons come from the ligand. It's still a covalent bond because it's still being shared, but all the electrons were contributed from the ligand, from the Lewis base. That's what makes this a special type of bond. They can form complexes and actual neutral compounds. These are all ions for the most part, 3+, 2+, +1, +2. Well, if they combine with a counter ion, you get what's called a coordination compound. It's just a bigger compound made out of the complex ion and then some other counter ion of opposite charge and the appropriate number of that ion. For example, here's the copper amine complex with a sulfate ion. They have the same charge, so it just takes one of each to pair together, and you get a coordination compound out of this. So how do you write it? Well, you still write the cation first, so I would write Cu, NH3,4, and then the anion, SO4. There's just one of each. Now, how do you name these? Well, you start by naming the cation, which happens to be the complex ion, and you first use how many of the ligand are present. Now, the NH3 ligand is actually called the amine ligand, and there's 4 of them. So we use the Greek prefix for 4, which is tetra, and you say that this is a tetraamine. And then what's the metal? Well, it's copper, and specifically it's copper 2. I know that because this is a neutral ligand. It's overall +2, so the copper must have an oxidation state of 2, a charge of 2. So this is tetraamine, and then copper 2 with a 2 in Roman numeral parentheses, and then the name of the anion, which is a sulfate. So you get tetraamine copper 2 sulfate. That's the whole thing. How about this one right below it? This is a chromium complex with a 3+ charge. Notice the chloride with only 1 negative charge means I need 3 of those chlorides to make a neutral compound. So the formula would be chromium, parentheses, NH3,6, and then Cl3. Now how do you name it? Cation first. There's 6 of the ammonias, so hexaamine, hexa meaning 6. This is a chromium 3+, because amine is a neutral ligand, so this is a chromium +3. So I would say hexaamine, chromium 3, and then chloride. It's still ionic, so there's no prefix for the number of the ion. There's prefixes for the number of the ligand, but not the ion. You don't say trichloride, you say just chloride. So hit pause real quick and try the third one. How would you balance this? How would you write the formula? What's the charge on the iron? And then what do you think the name would be? Okay, let's see how you did. So notice the 3 negative on the complex means I need 3 potassium ions in order to make this work. And potassium is the cation, so that goes first in the formula. So I put K subscript 3 and then the complex, FeCN with a 6. First up, name the cation. That's potassium. So the name starts with just potassium. Then I name the iron complex. There's 6 of the ligand, so we use hexa for 6. This is called a cyano. It's in the chart off to the right in that little table. So hexacyano. This is an iron, and I can figure out what the charge on the iron is by zooming in and looking at the complex. It's overall 3 negative, and each cyano group is -1. So I have 6 times -1 plus something for the iron, and it has to add up to -3. That means the iron has a 3+ oxidation state. That's a familiar oxidation state for iron, so it makes sense this would be an iron 3. And that's the complex. Potassium, hexacyano, iron 3. That's the whole thing. Speaking of iron, let's use that as an example to talk about why these things have a color. So it all has to do with the electron arrangement, the d orbital electron arrangement. Remember from the fall semester, if you want to look at the electron configuration for a transition metal, let's talk about the ion itself, Fe3+. Iron itself would have an electron configuration of argon, 4s2, and 3d6. But if you take away the 3 electrons, you would lose those outermost 2 electrons and 1 of the d electrons. So you're left with argon, 3d5. And in the gas phase, that's what an iron 3 cation would look like. 5 unpaired electrons all degenerate in the same energy level. But once you form a complex with ligands, the energy levels are actually not all the same. In this case, 2 of them are different than the other 3. They're very close to each other, but they're not the same. So if we use Hund's rule to fill them from low energy to high energy, I would fill my 5 electrons, 1, 2, 3, 4, and 5. I'd have some unfilled d orbitals in the same principal shell as these 3 d-filled orbitals. And then that's just a small enough gap that you can absorb light and excite 1 or more of those electrons to get a different electron configuration. This is just one possibility. And it's this gap that makes it different. We give names to these different states. The one on the left is called a low spin state. That's when you have fewer unpaired electrons. And the one on the right is called a high spin state. That's when you have more unpaired electrons. You can remember that by just looking at it and saying, oh, the high spin is when you have more in the high orbitals. That's not why it's called that, but it's an easy way to remember it. And then this energy gap we give a notation and a name for. It's given delta subscript 0, and it's called the crystal field splitting energy. It's the amount of energy that's absorbed by visible light, and this is why compounds and complexes made out of transition metal ions have such noticeable colors in the visible spectrum. It's because you can absorb wavelengths of visible light and excite these electrons from a low energy state to a high energy state. And we see that by what light is not absorbed, and it results in a color in the visible spectrum. So all transition metal containing compounds have a color associated with them. And it's all about this d electron arrangement. So let's close with calculating wavelengths of light and talk about the colors. Let's switch the compound. Instead of iron, let's talk titanium. To calculate wavelength, we're going to use this equation from the fall semester. The energy is related to the wavelength of light by Planck's constant and the speed of light. So let's say I know that this hexa-aqua titanium-3 complex absorbs this tiny amount of energy, 1 photon of that amount of energy, to excite its d electrons. What's the wavelength? Well, if I rearrange that equation and solve for lambda, you get lambda as hc over E. H, Planck's constant, is 6.626, 10^-34 joules seconds. C is 3 times 10 to the 8th meters per second, and the energy is given 3.9 times 10 to the -19 joules. You plug in the numbers, you get 5.1 times 10 to the -7. Check your units. The joules cancel, the seconds cancel, so this is meters. You could leave it like that, but most of the time we use nanometers for wavelengths, so just hit times 10 to the 9, and you get a couple hundred nanometers, 510 in this case. So what does that have to do with color? Well, 510 in the visible range shows up around there, in between green and yellow, closer to green. So if you use what's called a color wheel, you can look at what light gets absorbed and correlate that with what complementary color gets observed. The color we see is the complement to what gets absorbed. So if you draw a line straight through the color wheel where you're absorbing greenish light, that shows you what's observed. In this case, on the other side, kind of the red-violet. So what's absorbed and what's observed? Well, we would absorb green and we would observe a red-violet. So this titanium complex should look kind of red or violet in front of us because it's absorbing greenish light of that wavelength. Okay, so that's just a very brief overview of how we can calculate wavelengths and associate them with color for the absorption of energy, which happens as d electrons get excited, specifically in complexes of transition metal ions. This is even if they're just aqueous. Aqueous transition metal ions count as complex ions. And it's all because the d orbitals are at different energy levels once they form complexes, and there's a variety of different complexes made out of these cations and Lewis basic anions. Okay, thanks for watching.